Okay. Hello, everyone. My name is Naresh. I'm working as a senior researcher in the Laboratory of Nonlinear Optics at the University of Latvia. Today, I'm here to deliver my talk. The title of my talk is "The diffractive phase elements to form optical fields are driving with versatile spatial distributions." Okay. If I move on to the contents of my talk.
Okay. Hello everyone, my name is Naresh Kumar Readdy Andra.
I reported, I think so.
About recent work with the title.
How that's just the rise.
Okay.
You're trying again.
Okay, it's
Okay,
going.
it would. So let me. So wait. When it works.
Okay. The contents of my topic. So first, why do we need to transform the laser emitted from the source? And second, the second content is, so what does it mean by structuring of the light? And in order to transform the structure of the light, and we have investigated different kind of optical elements. Some of the elements I'm presenting over here, and they are binary optical elements, which are also called as a multi-sector phase plates, and the spiral phase elements and beam shaping elements, diffractive lenses and meta lenses. Finally, I will conclude with an applications. Okay, so why do we need to transform the laser emitter from the source? So generally, being as researchers, we are using a different kind of lasers in the laboratory. Sometimes we use a femtosecond laser, sometimes we use a nanosecond and picosecond, CW and pulse lasers. If you observe the profile of any laser coming from the source, the profile of any laser, it looks like a Gaussian distribution. But the laser, a laser which is driving with the Gaussian distribution is not desirable for many applications. So definitely you need to transform the shape of the laser from Gaussian to the desired form. For example, I'll explain you one promising application I'm presenting over here. So laser ablation is one of the promising application where Gaussian distributions are not expected by the researchers. For example, if you look at the first profile, it's exactly the laser beam with the Gaussian distribution. And the second one is a laser beam with a flat top distribution. So for example, if I use a Gaussian laser distribution for laser ablation, so most of the people who are working with the material processing applications, they are familiar about the laser ablation. Laser ablation is such a mechanism. If you illuminate the laser on surface of any target surface, and because of the laser energy, you can lift some amount of material from surface of the target. So if I use a Gaussian beam for laser ablation, so if I talk about the characteristics of the Gaussian beam, at the peak point, you can find a high intensity. If you're moving away from the peak point, the intensity is gradually decreasing. So if I use such a laser beam for laser ablation, so I cannot lift I can lift a material, but my edges are not smooth enough. So if I want my edges very smooth enough, so I don't need to use a Gaussian beam. I have to use some other specific structured beam. So then we have a requirement to transform the shape of the beam from Gaussian to the desired shape. So here what I did, I have just converted the shape of the beam from the Gaussian to the flat top. So flat top laser beam is such a laser beam. It is also called as a uniform intensity beam. So if you look at the profile of the flat top beam, it has a uniform intensity profile. The moment you illuminate the flat top beam on surface of the target material, because of the flat top profile, you can lift a material with the uniform edges. So the laser ablation is accurate and precise if you use a flat top beam instead of using a Gaussian laser distribution. So this is a one promising application explains us why do we need to transform the laser emitted from the source. So here I transform the laser from the Gaussian to the desired shape. My desired shape is a flat top. So here I'm presenting some of the desired structures. Like I have converted Gaussian beam into the rectangular flat top and square flat top and the donut flat top and also circular flat top. So if you talk about I have presented 4 different spatial shapes. So application to applications, you need to use a specific shape. For example, if I talk about an imaging application, in most of the imaging applications that people are using in a Gaussian beams. But if I use in a flat top beam will have a uniform intensity profile. The moment you strike a flat top laser beam on an object, on the object, light will give a uniform illumination. The moment light will give a uniform illumination, you can collect the information from the object with a uniform intensity. Then you'll present an image of the object with a high resolution, with a high axial and lateral resolution. That's an advantage of the flat top laser beam. So this is the one slide which explains that. So really, is it necessary to transform the structure of the laser beam from Gaussian to the desired shape? Okay, so what does it mean by structuring the light? So generally, the structuring of light explains something like that: modification of optical field originally emitted from the laser source. So if you're modifying the optical field which is originally emitted from the laser source, it is nothing but you're structuring the light. So what exactly you need if you want to structure the light? You have to control and manipulate the spatial and temporal dynamics of the light. So what does it mean by spatial dynamics? The spatial dynamics of laser is correspond to the amplitude, phase, and the polarization. So if you have an adaptive optics, or if you have a diffractive optics, which can control or which can manipulate the amplitude or a phase or a polarization, it means you're controlling the spatial profile or you're controlling the spatial dynamics of the laser. So what does it mean by temporal profile? The temporal profile of laser is a function of time and frequency. So if you have an adaptive optics, a diffractive optics, which can control the temporal profile of the laser, then you have a full control on laser. So basically, having an adaptive optics which controls spatial profile and temporal profile simultaneously, it is a very challenging task for researcher. So some researchers are targeting only in controlling the spatial profile and transforming the structure of the laser beam from Gaussian to the desired shape. Some are targeting on controlling the temporal profile of the laser by transferring the structure of the beam from Gaussian to the desired shape. So it is very interesting if you can control the spatial and temporal dynamics of the laser simultaneously. So in this piece of presentation, I'm not discussing anything about the temporal dynamics. So I'm not presenting any kind of adaptive optics. I'm not presenting any kind of diffractive optics which can control and manipulate the temporal dynamics of the laser. But only I'm presenting an adaptive optics and diffractive optics which can control the spatial dynamics of the laser. Thereby, you can convert the structure of the laser beam from the Gaussian to the desired shape. So my target is I have to manipulate and control the amplitude, phase, and the polarization. So I have to present such optics which can control the amplitude and phase and polarization. Thereby, you have a full control and a spatial profile. It means you're transforming the structure of the light from Gaussian to the desired form. Okay, so the first of all, I'm presenting the binary optical elements. So binary optical elements is a kind of an optical elements which are also called as a multi-sector faceplates. And these multi-sector faceplates and binary optical elements, which are very simple to use in experimental setup, and they are very easy to adapt in an experimental scheme, and they can easily manipulate the phase profile of the laser beam. Thereby, you can obtain a laser beam with a desired structure. So what is a working function of the binary optical elements? So binary optical elements, why we can call it as a binary optical elements? These optical elements can introduce either pi phase shift or zero phase shift for incoming laser beam. For example, I have a Gaussian beam. If I feed a Gaussian beam into the binary optical element, which is also called as a multi-sector faceplate. So multi-sector faceplates can introduce a zero phase or a pi phase shift to the different areas of incident light beam. And these sector plates can control the structure of the light, thereby to obtain a different intensity distribution in the focal plane. So if you look at this, the cartoon picture I have presented over here, they are examples of different kind of binary phase elements. And you can find over here, here I can find a binary phase elements with the 2 sectors. Here I can find a binary phase element with the 4 sectors. Here I can find a binary phase elements with the 8 sectors. So in these 3 diagrams, I have just distinguished the 2 different colors, like the black one and the white one. And the black one corresponds to the pi phase, and the white one corresponds to the 0 phase. So if I use such an element, if I eliminate the laser on this element, and this element can introduce either 0 phase shift or pi phase shift to the different areas of incident light beam, thereby the structure of the light beam is precisely converted to the desired shape. Okay. So what are the different kinds of binary optical elements we have? We have several different kind of binary optical elements. Some consist of 2 sectors, some are 2, some are 4, some are 8. So there is some classification as given. So binary optical elements with the 5 or more sectors can control the intensity patterns and the resulting intensity patterns with a bright center. However, other sector plates can form intensity patterns with the dark centers. There are 2 kinds of binary phase elements. You can control the spatial profile of the laser beam, and you can generate an output beam with a bright center. Or you can use such a binary optical elements. You can control the spatial profile of the laser, and you can generate an output with the dark centers. So you can classify the binary optical elements in 2 categories, like a binary optical elements can generate an output with the bright centers as well as with the dark centers. Why we are very much interested to use a binary optical elements? So because these sector plates have a high threshold damage. If they have a high threshold damage, so you can easily use for when you're dealing with the high power lasers, particularly with the femtosecond lasers. Okay, so I can present some experimental measurements what I recorded recently in ISSP with these binary phase elements. So you can have in a brief. Here I have given an experimental sketch over here. Here you have an femtosecond laser. Then we have a set of elements, and one is a quarter wave plate, and another one is the S wave plate. Then I have a binary optical element. Then we have a tilted lens. Then we have a CMOS camera. So if you look at the experimental setup is very simple. But here elements are very interesting elements. If you talk about the quarter wave plate, generally quarter wave plate which is used to transform the polarization. For example, if you want a laser beam not with a linear polarization, if you want a laser beam with a circular polarization, you have to use a quarter wave plate. So what is the use of S wave plate? S wave plate is something like a space retarded variant, and this is used to transform the polarization of the incoming beam from linear to the radial and linear to the azimuthal. So these S wave plates and quarter wave plates, which are used to control the polarization of the incoming beam. And the very interesting element I'm talking about here is BOE. That is a binary optical element. So maybe my binary optical element consists of 2 sectors. It consists of 4 sectors or 8 sectors. It doesn't matter. So how many sectors you have in a binary phase element? But simply this binary phase element will introduce a phase shift either 0 or a pi. Thereby you can get a different kind of structure. Now you can have a look on the first structure. So I have feeded a Gaussian beam inside a setup. As I have feeded a Gaussian beam inside a setup, maybe the polarization is a linear polarization or circular polarization. It doesn't matter. So the moment you feed a Gaussian beam inside a setup, then you have a camera. The camera is exactly placed at the focal plane of the lens. Here I have used a lens with a 150 millimeters focal length. So the moment you focus light in the CMOS camera, you can get such a picture. So if you look at this picture, the picture is something like a petal kind of structure. It's a kind of a spatial distribution with a petal structure. But if you look at the central area of this structure, you have a dark center. So for example, in your application, you don't need a laser with a bright center. You need a laser with a dark center. Then you need to transform the structure of the laser. So in such a cases, I can use a binary phase elements. So thereby I can transform the Gaussian into such a structure where I can see a dark center instead of a bright centers. Okay. So here I investigated the performance of the binary phase element in two different categories. One is on-axis focusing, one is off-axis focusing. So the first picture corresponds to the on-axis focusing. And what does that mean by off-axis focusing? The moment you tilt a lens, if you tilt a lens, the lens will include an aberrations. So tilting of lens will include an aberrations, then it is not called as an on-axis, it will be called as an off-axis focusing. So if you use an off-axis focusing with the same lens, so with the same BOE is giving a different kind of structure. You can see a different kind of a petal structure, and it is radially it is having some kind of an helicity. So this structure I obtained on off-axis when I rotated a binary optical element with angle of 180 degrees. If I keep on rotating an angle from 180 degrees to 200 degrees, then I transform a structure in a different way. So instead of getting in a dark center, I got in a compact intensity distribution where the center is at. So then you can understand that this element has such a flexibility. It will give you the laser distribution either with a dark center and also with a bright center. In on-axis focusing, it gives a dark center laser distribution. In off-axis focusing, it gives a laser with a bright center focusing. Again, if I rotated the same element with a 155 degrees angle, again I reproduce the same structure. This is a structure I obtain on axis focusing. This is a structure I obtain with off-axis focusing. The only difference is that here the BOE is rotated with the angle of 155 degrees. So that is a significance of binary phase element. Now you can ask a simple question. Okay, you have transformed the structure into a different kind of structure. Structures are very peculiar, very unusual and abnormal, where you can use these structures. So these structures can be useful in the fabrication of 3D values. If you want to fabricate a 3D values with using a laser with the versatile structures, this element can be useful. And these structures are also useful in the printing of some structures on surface of a material. So that is an advantage of the binary phase elements. Okay. This is one more piece of experimental measurements. Here I have changed the binary phase element. Instead of using the four sectors binary phase elements, then I just change the binary phase element from 4 sectors to the 8 sectors. So the moment you change a binary phase element from 4 sectors to 8 sectors, you got a different kind of structure and on axis. Now you found a different kind of structure. And if I ask the question, so where these kind of structures are useful, and these structures can be useful in exactly in optical particle trapping applications. If you want to trap in a particle exactly in a center, you look at the center, it's a dark center. The dark center is surrounded by the 4 high concentrated lobes. So these kind of structures can be easily used to trap the particle trapping applications. So this experimental result is correspond to the on-axis focusing. So if I move on to the off-axis focusing, I got very, very peculiar structures. The very, very peculiar structures. Some are look like a skeleton, some are look like in a very different kind of structure. So these are structures I obtained when you rotate the BOE, I mean the binary optical element with a different angle. So when you rotate, when the angle of orientation is 65 degrees and 99 degrees and 111 degrees, and you obtain 3 different kind of structures. We don't know, as of now, we don't know what are the applications of these 3 structures. Maybe in future we will find it out. But as of now, we only know the application of these particular structures. Okay, now. I'm trying to present one more piece of experimental measurements. So here we use one more binary optical element. It is not a circular one. This is the rectangular kind of binary optical element. So maybe you are unable to understand this binary optical element, but that is the reason I have presented some phase diagram over here. This is a binary optical element phase distribution recorded with using a phase interference spectrophotometer. And you can so see over here, this color map represents the phase levels of the binary optical element, and the phases are wrapped between the -pi to pi. And this optical element is also used to transform the structure of the laser. You can see here. So if you feed a Gaussian beam into this element, this element can transform the Gaussian beam into a different kind of distribution. So this is also a kind of a laser structure which can be used for particle trapping applications. This is the intensity distribution I obtained at the on-axis focusing, and these are two intensity distributions I obtained at off-axis focusing when you rotate the same BOE with a 50 degrees angle and also 90 degrees angle. So from structure to structure, the application is different. So when you have a facility to transform the structure of laser beam, and your application also differ. Okay. So after BOE, after binary optical element, then I have moved on concentrating on developing a flat top elements. So the flat top beam elements are also called as a laser beam shaping elements. So here you can look at the diagram, exponential diagram that we published in 2 publications already. And here you can if you pay attention on the first experimental sketch, we have a Gaussian beam, and you have a DOE which obtain a smooth phase profile, and you can see a phase levels are given in a different kind of colors. The moment you feed a Gaussian beam inside a DOE, and this DOE transforms the Gaussian beam into the flat top beam at a working distance Z. So after the working distance Z, again we propagated the flat top beam further, and we found this flat top beam has some sort of depth of focus. After that, it rapidly destroys. Because what is the difference between the Gaussian and the flat top beam? In a free space, Gaussian beam has an eigenmodes. But if you talk about the flat top beam is just an approximation. So the edges of flat top beam is very sharp enough. So the moment they start propagating, they distort very rapidly. So the depth of focus for the flat top beam is relatively very small when you compare with the Gaussian beam. Gaussian beam will have a long relic range compared with the flat top beam. But if you compare the applications of the Gaussian and the flat top beam, the applications of the flat top beam are significantly differ when you compare with the applications of the Gaussian. So that is the reason we have shown more interest in shaping of the beam from Gaussian to the desired shape. So in this picture, I have presented the DOEs for 2 different wavelengths. One is the wavelength for 1030 nanometers, that is called as infrared laser, and one is the 343, that is called as a UV laser. So I have presented 2 different DOE designs. These 2 designs can able to convert the beam from Gaussian to the flat top. If I look at the, I just wanted to explain one more interesting feature in this slide. If I use a short wavelength laser, these DOEs are capable to generate a flat top beam with more depth of focus compared with the flat top beam obtained for the longer wavelengths. So that's the specialty of these DOEs. And you can ask a question, okay, so how do you build these DOEs? In order to build these DOEs, and we develop a kind of a MATLAB algorithm. This MATLAB algorithm is based on a modified Rechberg-Saxton algorithm. And this algorithm is quite similar to the phase retrieval algorithm with a spatial filtering technique. And this algorithm is able to build a diffractive optical elements with very smooth phase profiles. So if you have a diffractive optical element with very smooth phase profiles, it is very easy to fabricate. Most of the challenging task in fabrication is if you don't have a smooth phase profile, you will find a lot of fabrication errors. If you have a DOE with very smooth phase profile, the fabrication process is very simple. So after this publication work, we just focus on concentrating and fabricating flat top beam. So recently we collaborated with one of the Institute of Physics in the University of Tartu. They have a nanofabrication lab, and we have supplied the phase data of the flat top beam, and they just use a maskless photolithography. They use a maskless photolithography in order to develop a flat top beam shape. This is a flat top DOE we obtained right now. It is not right now available in our lab. Now we are in a way to characterize this element to verify, to validate our simulation results. Whether really this element is capable to convert the beam from the Gaussian to the flat top with extended depth of focus. Okay, this is the optical microscope image of the flat top DOE, what we fabricated with using a maskless photolithography. And for each zone width, we have enough 100 microns. Okay, and this is a piece of information which needed to understand what does it mean by maskless photolithography. Okay, so later we concentrated on the digital optics. So probably, I don't know how many people are working on quantum technologies and neural networks, and also on nonlinear optics and harmonic generation. And the researchers who are working in this field of science, they are familiar about this kind of tool. And this is called as a spatial light modulator. This is a dynamic digital optics tool. It has a liquid crystal display. Okay. Okay, so what is the advantage of this tool? The advantage of this tool is that, so every time we will not find a fabrication facility to fabricate element. People are limited by the fabrication facilities because electron beam lithography and photolithography are very expensive techniques. Everyone cannot avail these techniques. So in such circumstances, what is an alternative? So you must have such a digital optics tool, which is called as a spatial light modulator. If you look at this kind of device, of course, the relatively expensive device, but it works very efficiently when you wanted to control the spatial and temporal dynamics of the laser. So if you look at this piece of box and you have a liquid crystal display, okay, it acts like a diffractive optical element. So what do you do exactly with this kind of tool? So see here, this is a kind of experimental setup I have used when I worked with a spatial light modulator. So there is a laser and you have an off-wave plate and you have a flip mirrors, then you have a beam expanding setup, then you have a beam splitter, and it splits the beam with a 50% to 50% ratio. Then you strikes the light, light strikes the SLM screen, then reflected back that you are projecting in the camera. Okay, this is a normal experimental setup which we use when we have worked with a spatial light modulator. So let me explain the simple way what is the advantage of spatial light modulator. See here, I have developed some face mask. This is a Axicon and this is a spiral Fresnel lens. Axicon is a kind of the diffractive optical element which can convert a Gaussian beam into the Bessel beam. So Bessel beams are a non-diffracting beams. So what does it mean by non-diffracting beams? Beams which can propagate over a longer distance in a free space in a turbulent medium without any intensity variation. And such beams are called as a non-diffracting beams. So it is a face mask I have simulated with a MATLAB simulation. This is called as a CGH, a computer generated holography mask. I have used this CGH exactly on SLM screen. So if I use such a CGS and SLM screen, the SLM screen itself is acting like an Axicon. The moment you strike a light on SLM screen, then the SLM screen is acting like an Axicon and it transforms the Gaussian beam into the Bessel beam. So you have a dynamic digital optics tool which acts like an Axicon. So if you don't want to use an Axicon, later I just I change a phase mask from Axicon to one more phase mask. That's a spiral Fresnel lens. So if you look at these two structured lights, these are two pieces of examples of two structured light. It's a Bessel beam, which is a non-diffracting beam, and it is called as a kind of a vortex beam with a topological charge of 1. Okay, so if you want a vortex beam with topological charge of 1, or if you want a vortex beam with orbital angular momentum, or if you want a non-diffractive Bessel beam, you need an Axicon and you need a Fresnel lens. So I can't fabricate two elements with available facilities, but I can use only one simple tool that is called as SLM. This SLM itself is act like an Axicon or a Fresnel lens based on your requirements. So I've also investigated some more phase masks like a spiral Fresnel lens with the L is equal to 5, spiral Fresnel lens with L is equal to 8. Here the topological charge is 5 for the structured light. Here topological charge is 8 for the structured light. So the conclusion is very simple. So if you don't have a facility to fabricate the diffractive phase elements, when you have a requirement to transform the structure of the laser beam, then you can make use of a dynamic optical tool called as an SLM. So the SLM is a simple tool which is very user-friendly and also customer-friendly. So simply, it is very easy to adapt in an experimental setup. So you can easily transform the structure of the laser beam from Gaussian to any desired shape based on your application requirement. Okay, how much time I have left?
Most of the earlier studies Two devices such as
Okay. Am I done?
No. Some minutes only.
Okay. 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 So recently I investigated one more piece of element that is called as a spiral phase element. The spiral phase element, which is widely useful in quantum communication and quantum technologies and neural networks, because this piece of element, which is used to transform the Gaussian beam into the vortex beam with orbital angular momentum. So, so these are the structures I have generated with the spiral phase elements with the 532 nanometers and with the 1064 nanometers. So the element works efficiently. So later I use this element in generating one experimental study. So I don't want to go into details because it has a lot of technical explanation, a lot of computations and analytics and also experimental measurement. But simply I explain you that the spiral phase element, whatever I developed, it is used to develop a demultiplexing of vortex laser beams with distinct orbital angular momentum. This is a piece of experimental setup I developed, and these are the experimental results I obtained. You can see that I have generated an orbital angular momentum beams with the different OAM modes in a configuration of 3 by 3. And here I generated an optical vortex beam with orbital angular momentum in a configuration of hexagonal. So these kind of beams are widely useful in a free space optical communication and also in quantum communications. So like a demultiplexing, you are just splitting of information into the multi-channels. It is quite similar to the wavelength division demultiplexing. Okay, the last part of my presentation. Apart from these diffractive phase elements, I have also concentrated on very hot theme of research, that is the metasurfaces, metamaterials and metalenses. So recently we developed a metasurfaces. This is a piece of experimental result published in a recent journal in IEEE Access. And this is the metasurface, which is made up of silicon metaatoms. These are cross-shaped silicon metaatoms. And this metasurface is acting like in a multifocal metalens. So what does that mean by multifocal metalens? For example, if I have an unpolarized light, if I'm feeding unpolarized light into the linear polarizer, which is the angle of 45 degrees, then you have a Gaussian beam with a linear polarization of 45 degrees. And that is feeding inside a metalens. The metalens is an example of it's an example of a metasurface which has a high diffraction efficiency and high efficiency in manipulating the amplitude and phase and polarization of the light compared with the conventional diffractive optical elements. So this metalens was able to transform the incoming beam into the multifocal spots. You can see the experimental result over here. So this is the result we obtained. Here you can see that there are 1, 2, 3, 4, 5, 6. I was able to form 6 focal spots at different distance. 3 focal spots are found by the X component of incident light, and 3 focal spots are found by the Y component of incident light. And it has a very high performance efficiency. The diffraction efficiency of this metalens is 95%. Usually, you will not achieve 95% diffraction efficiency with a conventional diffractive optical lens. It is only possible if you use a metalens which is made up of metasurfaces and metamaterial atoms. Okay, so these are the potential applications that are possibly these optical elements will cover. We can use these optical elements in laser ablation, optical tweezers, and optical communication, imaging, and the quantum computing, and also in a microscopy, because in all these applications, we need structure lights. Without structure lights, you can't generate any beneficial results from these applications. So definitely you need a kind of a new class of optical fields, a new class of structure lights. So that's it. Thank you. You have any questions?
Please. Yeah, so actually I use the spiral phase plates to produce a donut beam when we use optical levitation. But then we get the angular momentum is it possible to make a donut shaped beam by not having, but it's still with linear polarization?
It's possible.
It is,
Possible.
okay, can you make it for me?
Yeah.
Okay. Then I contact you.
Any more?
Is it possible to get a uniform distribution from Gaussian distribution?
Yeah, of course, this is what I presented, the flat top.
Still, it is not a complete distribution, it's complete uniform.
It is a uniform, actually. I've presented only the two-dimensional intensity distribution, but if you take a cross-section intensity profile, you can understand the flatness of the beam.
Is it theoretically possible to get
Okay, see that. These are diagrams I obtained from the simulations. So when you go for the experimental scenario is completely different. You will not achieve 100% flatness. You will see something like an 80% or 85% flatness. Even 85% flatness also, it's a very big achievement.
More questions?
Thank you.
No, thank you.